welcome to my class. In our last class, we have learned about various passive elements that we use in electrical network, their characteristics, their dynamics, and the equations that are associated with them and all. In today's class, we will be learning about various energy sources that we use in electrical network, and we know that energy source is another important component in electrical network or circuit. And in this series of lectures, this is our second class. So let's get started. Now, if we broadly classify the energy sources, then it will be one type of source will be DC source, and another type of source in our electrical network will be AC source. Now, DC sources are those sources where the values of those sources will be constant, so it will not vary with time. So DC sources, DC stands for direct current. So DC sources can be, again, broadly, if we classify them, it will be of two types. So one will be voltage source and the other type will be current source. So in be it voltage source or current source, their value, the amplitude of that voltage or current that is supplied by that corresponding source, that will be constant. Batteries and generators are good examples of voltage sources, whereas semiconductor devices like transistors are a good example of current sources. As we can see here, this is the symbol of independent voltage source that we will be using in our electrical network in our future classes. And this is the symbol of independent current source, DC source definitely. And this type of symbol we will be using in our electrical network. And this is an example of simple electrical network where we have used DC independent voltage source and DC independent current source. And definitely in that network we have 4 resistors. Then under DC source, along with independent sources, there is another type of source which is called dependent source. I will discuss more about dependent sources in detail in my future class. Now, for today's class, we will only know that dependent sources are those sources when the values of those sources, be it voltage or current, they are not fixed, and their values depend on some other parameters in that circuit. Parameters means here I refer the voltage and current, the responses in that electrical network, the voltage drop across any other element in the same network, or the current value that flows through any other element in the same network. And depending on that, the dependent sources can be again classified into 4 classes. One is voltage dependent voltage source. So here the voltage value of that voltage source depends on the voltage drop across some other element in the same network. Next type is current dependent voltage source, where the value of that voltage source depends on the current value that flows through some other element in that network. And in this symbol, we can see here that this is the input side, where the input current is coming from some other element, and this is the output side, which represents the value of that voltage source, dependent voltage source. So this is the symbol of current dependent voltage source. Now there is another parameter which is gain, and the value is 5. So it represents the voltage of this voltage source will be 5 times of the input current that is coming from another branch, or that flows through in that through that element in that same network. So it will be represented as V is equal to 5I, where I is the current that flows through this path and V is the voltage across these 2 terminals. Now there is another type of dependent source, which is voltage dependent current source. So this time this is a current source that will supply current to that network, but the value of that current will be dependent on the voltage drop across any other element in the same network. And this is the symbol of that voltage dependent current source. So here the input side, this is connected across any other element, and we measure the voltage drop across that element, and based on that we measure the current of that current source. So here the output current will be a function of the input voltage, and as we can see here the gain value is given as 2.5. so it will be the current value, the output will be 2.5 times of the input voltage across any other element. Now there is another type of dependent source, which is current dependent current source. So as it is clear that the output current will be dependent on the current value that flows through some other element in the same network. Now here this is a network where we have passive elements, and with that we have one independent DC current source, and with that we have a current source here. This is the output side of that current source, and the current value of this current source, it depends on the voltage drop across this resistor. So first the voltage drop across this resistor is measured, and based on that the current of this current source we get. So here as the gain is given as 10, so the value of this current source, if that is represented I as I, then I will be 10 times of the voltage drop. If that is suppose V, then it will be I will be 10 times of that V. Now next we will see the AC sources. AC stands for here the alternating current. So by alternating current, what we understand is the current here, it will not be fixed, or it will not have a constant value. Rather, one thing is that current will change with time. So it will be varying in nature or changing in nature, and it also has a nature, alternating nature. So by alternating, what we mean is the direction of current after a certain period or after a certain interval will be reversed. So as we can see here, these are examples of some alternating signals. Between this point and this point, we can see here a positive waveform, and between this point and this point we can see a negative waveform. The all other things are same, only the direction is reverse here. And between this point and the end point, this is a complete period where we have one positive cycle or positive part of that waveform, and again we have a negative cycle or negative part of that waveform followed by the positive part. And after this point, as we can see that the whole pattern, including the positive half and negative half, it is repeated. So that's why this type of waveform is also called a periodic waveform. So we know that periodic waveform, if mathematically we express that, then f of t, if it is mathematically expressed as f of t, a function of time, then it will be a f t plus nt, where n is an integer and t is the time period or periodicity. So after capital T times or multiple of that capital T, then that waveform will be repeating by itself. So if suppose n is equal to 1, then f of t will be f of t plus t. So after t seconds, we can say, or after t units time, the signal will repeat its type or nature. Now if we take n is equal to t, n is equal to 2, then f of t will be f of t plus capital 2 capital T multiplied by 2. So we can also see from here that after 2t times also, the nature or the pattern of that signal will be repeated. So this way, if we continue and if we take n is equal to 3, then we can also see that after 3t times seconds time also, the pattern of that waveform will be repeated. So one thing is clear from here, that in case of periodic waveform, the after a certain time, which is called or which is referred as time period or periodicity, the whole nature of that waveform is repeated. Now here we have another type of AC waveform, or periodic waveform, which is square. So it starts from here and then it is continuing like this, and then between this point and this point it has a positive half cycle, and then between this point and this point, which is same as the sinusoidal signal, it has a negative half cycle, and this is square in nature. Then after that, after this point, the whole cycle, the positive half cycle and negative half cycle, is getting repeated here. So both the signals here, sinusoidal signal and square signal, they have the same time period or periodicity. Now in this diagram here also we can see that between this point and this point the signal has negative value, and between this point and this point the signal has a positive value, and once it reaches at this point, suddenly it transits to the negative value, the negative peak, and then again it gradually increases, and at this point again it becomes it reverses. So this type of waveform is called as a sawtooth waveform, and there with in this diagram we are having another type of signal, which is actually a combination of several or multiple sinusoidal signals having different frequencies, and these frequencies are harmonically related with each other. So again here this is starting from this point and it is continuing this way till this, and then it is going to the negative domain, and the positive and negative half cycle has the same kind of nature, only the direction is reverse. Then after this point, as we can see, the whole pattern of this signal is getting repeated. So from this 0 to 6 within this time frame, here basically we have three complete cycles of this sawtooth and this signal, and between this point and this point, between 0 and 2, it has its periodicity or time period. So both the signals here also have the same periodicity. Next we will see a few terminologies that are associated with AC sources. Now here we can see we have a sinusoidal signal and it has one cycle of that sinusoidal signal. So from this point to this point it has one half cycle where we have the positive value of that waveform, and between this point and this point we have the negative half cycle where all the values are negative in that signal. Let's assume that this is a voltage signal where the amplitude of that voltage signal varies with time. The x-axis this represents time and the y-axis represents the amplitude of that voltage signal. The first terminology that we use or given here is in case of AC sources is peak value. The peak value is the maximum value that we get in case of AC signal in either side. So in case of positive side also, we have at this point the value of that signal is maximum, and in case of negative cycle also, at this point the value of that signal is maximum but with negative sign. In case of AC signal, in both the cycles, positive and negative half cycle, the peak value will be same. The difference will be in positive half cycle the peak value will be positive, and in negative half cycle the peak value will be negative. The peak value is represented by the capital letter and then suffix m, where m represents maximum value. Since it was assumed as a voltage signal, so it is Vm. Now the next terminology is instantaneous value. So it is the value of the signal or waveform at any instant of time. Since it is varying in nature, so at every instant the amplitude of that signal will be different. So instantaneous value gives us the idea of that about the amplitude of that signal at any instant of time. So we'll be representing that signal such a way that if we put the value of particular time, then we will be getting the amplitude of that signal. Now Since this was taken as voltage signal, an instantaneous value for every signal is represented by small letter, and since this is a function of time, it varies with time, so v a function of t. So since this is a voltage signal, so instantaneous value, and since this is a sinusoidal signal, so it will be represented as Vm sine omega t, where Vm is the peak value that we have already seen, and it is a sinusoidal signal. So sine and omega t is basically the theta, the angular measurement. Here the in that this graph, the signal is varying with respect to time, but it is the linear variation of that signal, but at the same time the signal will also vary angularly from its reference line. And when an AC signal linearly completes its time period, which is, suppose if it is represented by t, then angularly it will always complete 2 pi radian angle. Now suppose at this instant when the time is t1, if we want to know that what is the value of this signal, say if it is say v1, then what we will do is, in place of this sine omega t, definitely this sinusoidal signal will have a fixed frequency, so from there we will be getting the value of this omega, and now if we put the value of this t1, we will be getting the value of that signal or amplitude of that signal, which will be v1. So here at t2, which is basically, here it is the omega t value is pi by 2, because it is 1/4 of this total time period, so which is angularly 2 pi, so it will be pi by 2. So if we put this pi by 2 here, then we will be getting the amplitude of that signal, and if we represent that as v2, then pi by 2, if we put here, then sine pi by 2, we know that it is 1. So the amplitude of that signal at this point, at this instant, will be only Vm. That means the peak value or maximum value, and that's what we are getting here in that waveform. Now at this instant, when we have negative half cycle, so if we put the value of this time in the same expression, then we will be getting the amplitude of that signal, along with there will be a negative sign. Similarly, for T4, if it is another instant, then we will be getting another value for that signal. The next terminology that we use in case of AC sources is average value. Now to get the average value of an AC signal, what we do is, first we vary the time by a small amount, and that variation of time we take as, or we represent by dt, and then we calculate that how much area is covered by that AC signal over that time. Now since this is a very small time that we have considered, next what we do is, those small areas, for those small variation of time from the initial time to final time, then we add all those smaller areas to get the overall area of that AC signal, and then we divide that whole area covered by that AC signal by the total time, or we can say time period of that AC signal. So symbolically or mathematically, how we write is, first xt dt. So xt is the signal value or that amplitude of the signal, and then that is multiplied by the small interval of time that we have mentioned here by dt, and this we multiply, when we multiply this two, then we get the area which is covered by this smaller portion under that curve, and then when we integrate over a larger time, then we get the total area covered by that particular curve over that time period. So, and then we divide the total area covered by that portion of the curve by the total time. Now one thing here we can notice, that when this is the general representation of the average value for an AC signal, now when we find the average value of a sinusoidal signal, here we have considered only pi, though we know that for a total time period, the angular displacement or angular movement of an AC signal is 2 pi. but here we have only considered between 0 to pi. The reason is when we will find the average value for a positive half cycle for that sinusoidal AC signal, the average value that we will be getting for this positive half cycle, the same average value we will be getting for the negative half cycle as well with a negative sign. So if we consider the total time period or for the total periodicity, then the average value, whatever the value is, that will have some positive value, and for the negative cycle it will have the same value with negative sign. So they will cancel each other, and finally the average value for any kind of AC signal, be it sinusoidal or any kind of non-sinusoidal signal, the average value will always get as 0. And that's why when we calculate the average value for an AC signal, we only consider the half of the time period. And that's why in this expression we have considered only the time period from 0 to pi. And when we divide, we have divided here the total by the total time period, there also it is, instead of 1 by 2 pi, it is only pi. Now in place of x of t, we have here put the expression of the sinusoidal signal, which is Vm sin omega t, and that's what Vm sin omega t. And here, since pi is the measurement of the angular displacement, means that is the measurement of theta, so here the integration is not only with respect to t, rather it is, this integration is with respect to the omega t, or we can say the theta value. And if we follow the rule of integration, then finally we'll be getting this minus Vn cos omega t, and this is a definite integral which varies between 0 to pi, and already we have 1 by pi, that factor. So finally it will be 2 Vm by pi for sinusoidal signal, and if we simplify further, then it will be 0.637 of Vn. So average value of a sinusoidal signal will be 0.637 times the maximum value or peak value. Now for different signal, the average value will be different. For square signal, as we will see in the next slide, it is 1, and for other signals it will have different value. Now there is another terminology which is called RMS value, root mean square value. This RMS value, in case of AC signal, as we have seen, that it is not fixed like DC signal, and at every instant the amplitude varies. But sometimes we see that when we talk about AC signals, sometimes we represent as 220 volt AC or 230 volt AC. Apparently it may seem that it as if it is a fixed value that by which we are representing the AC signal, but that is basically we refer as the RMS value. So RMS value we can say as the effective value of any AC signal, which is measured in terms of its heating power. So in case of AC signal which is varying in nature, RMS value is the effective value, or we can say it is the equivalent DC value of that AC signal. Now how to find the RMS value? So root mean square. So here, since we'll be taking the square value, so there even if we consider the negative half cycle and the negative amplitude also, since we will be taking the square value, so it will finally become positive. So here, to get the RMS value, we can consider the total time period instead of the half cycle or half time period. So here it will be first the square value of that signal, so Vm sin omega t square, and then we will be definitely integrating with respect to d omega t. So first we will consider for a small time duration, and then we will be integrating, or we will be adding over the total time period, and then we will take the mean value. So we will divide by the total time period, which is for AC sinusoidal signal, it is 2 pi. So this way, first we will calculate the mean value, and then finally we will take the square root of that mean value. And that's how we have written here in this expression. Now if we follow the rule of integration, then first this Vm is constant with respect to omega t, so it will come out of the integration. Now this sin omega t, what has been done here, this it has been expressed as, since this will be sin square omega t, so half has been multiplied, and then this sin square theta or sine square omega t has been converted to 2 sine square theta. Now 2 sine square theta finally has been represented as 1 minus cos 2 theta here. Then we have performed the integration, and finally if we put the limits, then it will come as Vm square by 2 and then square root value. So finally it will be Vm divided by square root of 2, and square root of 2 means 1.414. So finally it will be 0.707 Vm for sinusoidal signal. For other signals, they will have different values. Next terminology is phase angle. Phase angle is the angular measurement of the position of that AC signal or wave. As I said in this diagram, it is expressed as a function of time, but angularly also there will be displacement from the reference line, and for over a time period of periodicity, the total angular displacement is 2 pi radian. Now this red color waveform is our VA, which is starting at 0, 0 point, where time is 0 or omega t. The theta value is also 0 here, and the amplitude also 0. So from this point to this point, it has the positive half cycle. So angularly we can say this is pi radian, and here it has the peak value, so we can say angularly it is pi by 2. Now from this point to this point, it has the negative half cycle, so it will be finally 2 pi. So from this point to this point, the angular measurement will be 2 pi, and from this to this, the angular measurement will be 2 pi minus pi, so pi. Now it has the negative peak here, so it will be angularly it will be 3 pi by 2. Now this red colored waveform has been taken as a reference, so it has been represented like Va is equal to Vm sine omega t, the instantaneous value, as we have seen earlier. Now here we have another waveform which is represented in blue, and we can see in the diagram that as if the blue, this signal has been this is ahead of the red signal, so it has started before this signal, the reference signal. So phase wise we say that this has a leading phase. The difference between these 2 points angularly, it is theta. If it is theta, then that will be represented as Vm sine omega t plus theta, and that will be the instantaneous value of that signal. So this blue signal is our Vc. Now we have another signal which is represented in green, and we see here that this signal is starting after red signal. So phase wise we can say that it has a lagging phase. So since this green signal is starting after this red signal, so we can see as if this is a delayed signal. So delayed signal means the phase wise it will have a lagging phase. And again, if this phase we represent by theta, the difference between these 2 points angularly, then the instantaneous value of that signal will be represented as Vm sine omega t minus theta, since it has a delayed phase or lagging phase. So this green waveform is the signal Vb. So this is how we represent the instantaneous value of a signal when we take that as a reference, when a signal that has a lagging phase with that reference signal, or a signal that has a leading phase with respect to the reference signal. Now next terminology is form factor. In case of two AC signals having same frequency and peak value, they may look different because of their different configurations. Now this form factor represents that change in configuration, and form factor is the ratio of RMS value of that signal and average value of that signal. RMS and average value we have already seen and calculated. So for a sinusoidal signal, the RMS value was 0.707 of the peak value, and average value was 0.637 of the peak value. So if VM since is the same parameter, the peak value of the sinusoidal signal, so they will cancel each other, and this ratio finally will have value 1.11. so the form factor of a sinusoidal signal is 1.11, and for a full rectified waveform, also sinusoidal waveform, the form factor is also, we can say, 1.11. For half wave rectifier, the form factor is 1.57. For a square wave, it is 1. For triangular and sawtooth, it is 1.1547. In our next class, I will discuss more about for triangular and square wave related to form factor and peak factor. Now, peak factor is the next terminology that we frequently come across in case of AC sources, and it gives an idea about the sharpness of the AC signal, or we can say how much that AC signal is deviated from its equivalent DC value. Equivalent DC value, we have seen earlier that it is actually the measurement of RMS value. So peak factor, which has another name, which is crest factor, it is the ratio of peak value and RMS value. So it gives an idea that how much that peak value is deviated from the equivalent AC value or RMS value. So for a sinusoidal signal, it will be Vm simply divided by 0.707 Vm, which is the measurement of RMS value. And finally, it will be 1.414 for sinusoidal signal, or for full wave rectifier. For half wave rectifier, that value is 2. And for square wave, it is again 1. And for triangular and sawtooth, it is 1.732. Now, in this lecture, we have learned about different AC signals and different terminologies like peak value, instantaneous value, average value, RMS value, different factors like form factor, peak factor. Also, we have got a brief idea about phase angle. So with this, I end today's class. Thank you.